exothermic reaction. Energy level diagram. Remember, for exothermic, there is a heat that is released. So, the reactants are of higher level. So, this is reactants. Then we have products. But there is what we call activation energy. So we have products. That is the activation energy, the EA. Now, this difference is what we call delta H. And for exothermic reaction, delta H is negative. Reason being that products, remember, heat change is heat of products, enthalpy for the products, minus that of reactants. And for exothermic reactions, the product, there is that heat that is lost. So the energy for the products has to be less than that of the reactants, because heat is lost to the surrounding. And that is why you get the difference is negative. So our delta H has to be negative. For example, if we have the enthalpy of the products to be 23 kilojoule, then that of the reactants maybe to be 53 kilojoule. Now, our delta H has to be that 23 minus 53, which is exactly negative 30 kilojoule. So that is enough to show us that indeed there is a negative delta H. So we have said that is negative 23 minus, that is 53 from 23, and that gives a negative 30 kilojoule, confirming that the reaction is exothermic, thereby having a negative delta. So we have said in an exothermic reaction, the reactants change to products by evolution of heat. Hence, the products have a lower content, a lower heat content than the reactants. And for this reason, we have confirmed that delta H has to be negative, since H2, which is that of the products, is less than H1. H1 for the reactants, H2 for the products. So this is reaction path or progress. Then this is energy. in kilojoule. For temperature changes in an exothermic reaction, the heat lost is absorbed by the environment, or rather surrounding, making the final temperature to be higher than the initial temperature. So we are saying that is T2, which is for the final, is greater than T1, which is for the products, or simply a reactant. T1 for the reactants and T2 for the product. Sorry for that. And we have said T2 has to be greater than T1, which is the initial, and then T2 is our final. Let's look at the second case, that is endothermic reaction. For endothermic reaction, reactants change to products by absorption of heat. Hence, the products are at a higher heat content level than the reactants, implying that H2 is greater than H1. Remember, H2 is the heat content of the products, then H1 is the enthalpy of the reactants. So because the difference between product and reactants is bringing some positive value, then we conclude that endothermic reaction has to give a positive delta H, that is positive enthalpy change. It is product minus reactants, but that of the product is already of higher energy compared to that of the reactants. So the difference has to be positive, and not negative like for the case of exothermic reaction. Now, we are saying that in this case now, there is heat that is gained or absorbed from the surrounding. And that is what is making. Now, there is heat absorbed. So, the surrounding must have a lower one compared to the reacting vessel where the substances are reacting. So this is how the endothermic energy level diagram will look like. So the reactants are of lower level compared to the products. So that is reactants, products. So you can see that heat is taken in, the heat is absorbed, and that is why we can have a positive delta H. So when you take now H2 minus H1, we realize that is a positive value. Not like in exothermic that is giving out a negative value because of the fact that product energy is lower than reactant energy. That is all about endothermic and exothermic reactions.